Thank you. All right, so today, as usual, since the exam is on Wednesday, we will review by going over the practice test. So I just have it up on the screen since, I'm recording it. But of course, the first page is definitions. So, there's going to be same on the exam, not the same words, of course, but you'll have a sheet with your definitions on there. Okay, and then we'll start then with number 2. And okay, so this question is telling you that you're given the synthetic routes and that they are not necessarily the best. Okay, so they're inefficient. Doesn't mean they would not necessarily give you this product, but they may not be the best way of doing it. And what I want you to do is to think about it and suggest how to change it. So you can decide that you want to change the reagents and keep everything else the same. You may want to change the starting material, to give you the product using the reagents you're already given, or you can change, like you said, some condition about it that you may think is better. The only thing you should not change is the products. Does that make sense? So you want to make what you're given, but you can change anything else about it that you see fit. Does that make sense? So what's going on with the first one? So I guess the first thing is to think about why wouldn't this give you what you want as a product? What's the issue with this here?
That kind of substitution can't happen.
Yeah, so this is a substitution reaction, right? We're substituting, again, you're leaving group the bromine, right, with your methoxy, right, the ion, to give you that product. But this is assuming what mechanism?
It'd be SN2.
SN2, right? But can I do SN2 with the starting material I'm given? I cannot, because it is what? Tertiary, right? So this carbon here is tertiary, which would not allow for the reaction to go like this. So what would I need to do? So what can I do?
Make it a primary carbon. I have the bromine coming off of primary carbon.
But I still want this, right? So
could you make it coming off and then have distribution?
So as it's drawn, it's going to lead to elimination, right? Because this is a tertiary. This is acting as a base, right?
Yep.
Not as a nucleophile. That's the point, right? We should give you an alkene, but that's not what I want. I told you I still want you to make this. So what mechanism would I need to make this go in order for the product to work this way? SN1, right? So you want to switch this, right? So you want SN1, right? Not E2, right? Which is what's going to happen if you follow. So what would I have to do to the reagents? I'm not going to change the starting material in this case because it's important that the substitution be at the carbon that it's at. And it is a tertiary carbon. So how can I make this SN1? So what's the important thing for an SN1 mechanism?
A strong nucleophile. And
The nucleophile is not that important. But I don't want it to be a base, right? The strength of the nucleophile is not a big deal, but I don't want it to be a base. So if I want to add this, but I don't want it to be a base, what should I get rid of over here? The sodium, right? I want it to be the alcohol. Does that make sense? Because now it's not a base anymore, right? This is neutral. Right? And then what else is important in an SN1? The solvent, right? What kind of solvent promotes SN1?
acid.
So something that is polar protic, right? Okay, so you want in, right, a polar protic solvent. And you don't have to specify, give me one specifically, right? And actually alcohol, right, the methanol is a polar protic solvent if you think about it, right? It's polar and it has a hydrogen, so does that make sense? But this is what you would need for it to go SN1. Does that make sense? Because the way you have it, it's going to want to go the elimination route. Does everybody understand that?
So it wouldn't even make that product.
It would not. It would make an alkene. The way it's drawn, this would have to have a double bond here. So it would not substitute. So in order to substitute, I don't want a base, right? The base is kind of what's making this go elimination. We've talked about that, right? That kind of the fact that a base is also a nucleophile, so that can be something, right, that leads these to be competing mechanisms. But does that make sense? What is wrong, right? So you kind of want to identify what's wrong for yourself and then figure out, okay, I still want to get that product. Does everybody understand? So don't change the product. I want you to still be able to give me the product if possible, right? So I'm hopefully giving you ones that you can change. So what would I want to do in B? So what's wrong with B?
It's your reagent wants you to have the aldehyde form of the product, right?
Exactly, right? So what I want here, right, is an aldehyde. But the way I have it, what should it give me? This is a primary alcohol, right, with chromic acid. So what would that give me?
Reaction sheet.
Yeah, reaction sheets would be great. Right? Remember, you're not just sitting here copying my answers. We talked about that last time. Okay, yes, I'm here to give you the answers and help you through this, but you're supposed to be thinking about it, right? So get out your reaction sheets and think about it. What is the chromic acid, right? It's going to give me, the way it's drawn, right? It's going to give me, should give me a carboxylic acid, and I don't want a carboxylic, right? I want an aldehyde. So what's the reagent that gives me an aldehyde? PCC, right? So I need, right? I want an aldehyde, right? Okay, so I need to change the reagent, right? So to PCC. Does that make sense? Because PCC always, right, when you have a primary, it gives you the aldehyde. It's on your reaction sheet, right? So if again you understand how to use that, that's an easy question. Does that make sense? Don't make it harder than it is, right? In a situation like this, it's really just thinking about the reagent. Does that make sense? The next one is an epoxide. The way the epoxide is given there with the reagent, right? So what kind of reactions do epoxides do or undergo, excuse me? So they're also substitution reactions, right? And they're SN2 type mechanisms. Remember that the nucleophile, right, should attack, right? And then the oxygen carbon bond opens up like a leaving group. It is not technically leaving, right? So you're still going to get an alcohol. Does that make sense? So this being here, right, is from this part, right? So what is your nucleophile in this situation here? Chlorine, right? So the Cl is the nucleophile, but is HCl acting as a nucleophile? Does HCl qualify as a nucleophile. It does not. It's an acid. Right? So yes, I want chlorine. Does everybody understand that? But what's the problem? The reagent as given is not going to do what you want, even though there's a chlorine. So how do I want my nucleophile, the chloride ion, to be presented? So you want, right, Cl minus, right, as a nucleophile. So how do I present that?
Oh, it's a sodium.
No, in
As what?
H3O plus.
Yes.
H.
H.
What'd you say?
I said with the sodium.
With the sodium, right? As
Yeah.
sodium chloride, right? So sodium chloride, right, substitutes the HCl. Right? Because all the HCl is going to do is do an acid-base reaction, a protonation at the oxygen. It's not really, right, designed to do a substitution, a SN2. Does that make sense? You need a strong nucleophile. So again, it's a very easy change, right? And it seems like, okay, right, this isn't so bad, but you have to think about what's going on. So what about D? What's wrong with D? Right, and if this is confusing, you can always draw it out for yourself, right? This is a CH3, right, in the parentheses, 3, so it really looks like this. Right, that's actually the starting material, so if that parentheses is confusing to you, right? And again, you can do the same thing here. Right? So what is happening here? So you're taking a double bond, right? You're doing an addition reaction and adding what?
No H.
An OH, right, plus an H over here, right? So this is really, right, a hydration reaction, acid catalyzed hydration of an alkene. So what's wrong? What's my problem here?
That would
Right, because
just give it
these
more
reagents,
H's.
right, this is acid catalyzed hydration, what would happen?
It would just fill up. It would just take away the double bond.
It does. It takes away the double bond. It adds the OH. It's following Mark's rule. But what's the problem? Is this really the major product?
No.
No, because this leads to what?
It
It's like
resonance.
hangman. It starts with an R.
Resonance.
Not resonance. Rearrangement, right? So acid catalyzed hydration should be a little note on there that rearrangement is going to happen anytime that it can. Isn't this side over here, right, an issue? Issue meaning rearrangement can happen, right? So if we take the double bond, right, this is what my nucleophile, or excuse me, my cation would look like, right? But that's not really what's going to happen, right? Because what?
One of the metals is good.
Yeah, right? You're going to have a shift. So actually the product should be here, the OH, right?
Yes.
Okay.
Where would that methyl go? What would it look like?
Yeah, so one of those methyls is going to shift to where the carbocation is. So that's what's
And
going to end up happening
The
there.
bromine
So-
goes. I mean the.
And then the
Alcohol.
OH should actually be here.
Do you have an extra card?
So, do I have an extra carbon?
Yes.
Ah,
Yeah, you do.
that's why it looks funny, huh? I'm sorry about that. I'm so sorry. Made it more confusing than it should. I'm sorry. Right? Sorry about that. So basically one of these, right, is going to come here, right? And so like I said, then this OH shouldn't really be here because the CH3 would be here, right? And the cation would have been then on the carbon next to it, so the OH should have been here, the way it's drawn, right? If rearrangement is possible. So is there a reagent that does not allow for rearrangement? Yes. So I don't want rearrangement, right? Because I want that product. So what's the reagent that does not give me rearrangement? It still gives me an alcohol. What is the reagent? CO2. Because that's going to give you a Cl and an OH. I just want an alcohol. There's 3 alcohol
A
popular.
BH3?
BH3, right? BH3 should stay on your reaction sheet. Everybody look at their reaction sheet. Because this isn't going to help you.
But it's
Not the BH3.
It's anti-mark.
So what is the other one? So there's hydroboration, there's acid catalyzed, and then oxymercuration. So it should be the oxymercuration. So there should be 3 types, right? One gives you rearrangement and one does not. So look at your reaction sheets. Can you see what I'm talking about?
Oxymercuration, it's Marshall, anti.
And then it should say somewhere, well, this isn't the right reaction sheet, so. Right? We're supposed to be in the alkene reaction sheet.
I got it.
So, I mean, you know, the reaction sheets aren't going to be helpful if you don't know how to use them. So please, who has the right reaction sheet?
It's oxymercuration
Okay.
followed by reduction.
So it should be the oxymercuration, so it's Hg with the acetate, right? This followed by what?
H2O. And then underneath the arrow is NaBH4.
Reduction.
Reduction.
Right? So again, if you're dealing with a double bond, you need to be on the double bond reaction sheet. So remember that all the reaction sheets from last semester should be coming with you to the exam as well. So this is from chapter 6, I believe. Okay? So there should be, again, 3 types, right, of hydration reactions. This isn't the right one, right? Right, so you want to change, right, your reagent to this one. Because, right, it does not give you the rearrangement. Does that make sense? So number 1, you got to have all of the reaction sheets. Go to the Blackboard site. All of them are listed there. Go ahead and print all of them, even the ones we haven't done yet. Have it as a little packet for yourself. You know, that's going to make your life so much easier rather than flipping back and forth and pulling it from here, pulling it from there. Have it as a little packet. And then as we learn a new chapter, it's already there. And you always have the older ones, right? Because those are going to pop up just like this. Okay. So again, and if you don't practice the reaction sheet, they're not going to be that helpful when the exam comes, unfortunately, because you're not going to really know what to look for. Okay, so that's number 2. Does everybody understand? So, question like this on the exam, again, right, is asking you to think about, okay, you've seen all these reactions before, but it's about identifying the mechanism. And then there's slight difference between reagents. So you have to, be aware which reagent would actually be better for this kind of mechanism that you're asked. So do you think a question like this is going to be on the exam?
Yeah.
Do you think it's going to be exactly these?
No.
No. Close to it.
Am I going to be in trouble?
Yes.
It's okay. We got to study this.
So that's what I mean, like when you're studying, you should actually change these up a little bit to see if you really understand. Go ahead and make that double bond somewhere else, right? Give yourself another product and see, hey, would I be able to figure this out? So, okay, so that's number 2. Number 3, hopefully, It's a little bit more straightforward. So it's giving you these two alcohols. So you have cyclohexanol, pKa of 18, and then you have a phenol, pKa of 9.96. So the question is, why is the phenol, right, considerably better acid or stronger acid than the cyclohexanol? So what's playing a role here?
The aryan
The
green.
double bonds, right? And not just any double bond, but the conjugated, right? So the benzene double bonds are conjugated. So remember that they spread themselves out anyways, right? The double bonds belong to all of the carbons. So if you have this O as an O minus, right, which would happen if you did an acid-base reaction, now you can actually extend this conjugation up, right, and draw that negative charge, which is what stabilizes the anion. Does that make sense? So this has to do with not just a double bond, but the conjugation, right? So these are conjugated double bonds. Right? And your goal is to spread the anion, right, the charge, right, the negative charge throughout. That's why having a bigger, right, having a bigger atom, like comparing oxygen to sulfur, there's more, right, spreading capability. With the conjugation, there's a lot of that, and there's no, right, possibility for that in the cyclohexanol. There's nowhere for the charge to go, so it is not really considered to be a strong acid. Does that make sense? Again, hopefully that's more straightforward, right? Still got to consider, right? Remember that in general, alcohols are not good acids. They're not acids, they're not base. They're right in the middle like water. They're neutral. Okay? So then in B, it talks about, right, boiling points. So what do we know about alcohols and boiling points and what alcohol?
The more OHs, the higher the boiling point.
Yeah, so the OH, right, provides more hydrogen bonding. Okay, but also the chain length matters too, doesn't it?
Yes.
Yeah, so the longer your chain, what happens to your boiling point?
It gets higher.
Also goes up, right? Because you have more bonds that you have to break, right? Theoretically, to make the alcohols into a gas form. So what would we think about this? What would be, so we want increasing boiling point, right? So which one would have the lowest boiling point? D, right? Which is not even an alcohol at all. Remember that alkanes are not, right, the boiling points are not very high, right? And then what would be the next one? B, right? So then it would go up some, right, significantly to 78. One alcohol, then what else?
Oh.
So then, sure I have this here. Yeah, then A, right, it's a longer chain.
And C would be 198, says.
Yeah, and then this, again, the more OHs you have in your molecule, then the more you'll have the potential for hydrogen bonds between the molecules. Does that make sense? So you can put the numbers in, or you can list them like D, right, increasing order. So then D, B, A, C. Does that make sense? So depending on how the question, I don't always give you values. Sometimes I just ask you to look at it and tell me the order. Does that make sense? And if it was in a decreasing boiling point, then the order would have been opposite, right? C, A, B, D, the higher first. Does that make sense? So that, right, that increasing boiling point, it could be same ones and stay decreasing, right? Or I may just change slightly again. That's how I know you really learn rather than just memorize. So I like to do that. So that's part B. And then C gives you pairs. So I want you to select now solubility. So what do we know about solubility with alcohols?
They're very soluble.
Very soluble because
Of the hydrogen bond.
they can hydrogen bond, right? So again, another, right, effect of hydrogen bonding. And again, you want to consider. So between A, there you have the chlorine, so dichloromethane versus the alcohol. Right? Alcohol, this is actually non-polar solvent. So, what about in B? So remember, ET is what? Ethyl, right? So this is actually what? An ether,
ethanol.
right? Remember that ethers, they can't hydrogen bond, right? So, again, you should go towards the alcohol. So what about in C? An ether versus a carbonyl.
Carbonyl. The carbonyl.
The
is-
carbonyl, right? Because the CO double bond is a dipole. Right? That doesn't happen in the ether. So there's a little bit more, right, ability to interact.
So you're
And then
saying,
in D,
ethers can't.
well, they still have lone pairs, so water can come along and be the hydrogen donor. If you have no oxygen at all, you're really out of it, right? But between these two, right, this can do this also, but there's no charge dipole separation, so the water will be drawn to the carbonyl more so than the ether. Does that make sense? So in this case, it would be the oxygen. That's number 3. Does that make sense? So again, thinking about those physical properties that we talked about, boiling point and solubility. And 4 is naming. I'll give the name here. So what do you think of the first one? What should I look for here? My functional group, right, which happens to be what here?
Propyl.
That's not a functional group.
Oh, that's a benzene.
And not just the alcohol, but the
Polyamine.
phenol, right?
Phenol.
A benzene with an OH together, that gets its own functional group, and it's called the phenol. So now we've already named the benzene and the alcohol, so what's left?
The propyl.
The propyl, and the propyl is where?
3.
Because the O, right, the carbon attached to the OH is always number 1 in a phenol, right? So this would be 3 propyl phenol. And you don't have to say 1, because in a phenol, it's always going to be 1. If you put the 1, I'm not going to penalize, but it's not necessary. So what's B?
That looks like an
So
ether.
unfortunately, that's one of those you just have to memorize, right? Which one is it? Oxalane, right? This is oxalane. Or you can also call it THF, which is tetrahydrofuran. That's the common name. And I mean, this is a common solvent, so that's why, we see it all the time. Just call it THF. But oxalane, I remember that you have oxirane, right? Oxetane, oxalane, and then the dioxane. Oxane is another, and then dioxane. So unfortunately, there's not too much rhyme or reason for those, but it is the ring size. So, and then what's C?
2-methyl 1-propyl.
So it's a thiol, right? So again, the functional group here, right? So this is carbon number 1, 2, 3, because the functional group gets priority. So 2, there's a methyl, right? And then it's 1 thiol. And you do have to say 1 because the thiol could have been a carbon 2.
But how do you specify that there's a 3-carbon chain?
That's it?
Oh. Yeah, I kind of skipped the big step, didn't I?
Propyl thiol?
Propane.
Oh,
Remember, you keep the E just for pronunciation. Usually we drop the E and add the ending, but for pronunciation we keep the E there for the thiol. Sorry, totally jumped a step there. Yeah, so 2-methyl, then the chain, right, propane, and and then thiol. But you do have to identify where the thiol is, because it could be at another carbon in that chain. On the next part, now it's an alcohol. So just one alcohol. So again, if this is confusing you, right, just draw it out. So here's a CH3, right, with 2 there in the parentheses, right, and then the OH is coming off of that carbon as well, right, and this one again has an OH and an H, and then it's attached to a CH, which again has 2 CH3s. So if it helps you again to draw it out, right, those parentheses might be a little confusing. So the carbon, right, to the left has the OH, their substituent. So this is called what? Longest chain is? So 1, 2, 3, 4, 5. Does that make sense? And then I do want to give my alcohols the lowest number possible. So I think if I start on the left, that first OH is at 2. Right? So if 5 is my longest chain, then I have a substituent at where? 2, right? And 4. Does that make sense? So this is 2,4 dimethyl. What else? So then you gotta do where the 2, 3, and then it's pentane again. I'll never forget. Right? Or penta, you can do it either way, but it's diol at the ending, right? To say that you have 2. And again, you leave the E in there just for pronunciation. It's just so 2,4 dimethyl, right? 2,3 pentane diol. And what about E? E is what? So it's that analog of an ether, which is called a sulfide, right? And you can do the common name or you can do IUPAC. So the common name, what do? I name both sides as substituents. So this would be ethyl, propyl, and then you just say sulfide. Or, right, you can do the IUPAC, which like the ether takes the smaller of the 2, right? 2 carbons is smaller than 3 carbons, and it puts it together, right, with the sulfur, so it becomes ethyl sulfonyl. Sulfonyl. And then propane. Right? The bigger chain becomes the parent name. Oh, sorry, and it is 1. Because it's coming off of the first carbon, right? This could be coming off here, and then it would be 2 ethyl sulfonyl propane. Makes sense, naming? Again, make sure you practice, right? The one specific. This is not one that I'll go back to other functional groups or anything like that. So you want to practice the alcohols, the phenols, the ethers, the thiols, the sulfides. Oh, and the epoxides, the cyclic ethers. And then there might be double bonds in there, or triple bonds, so you do want to do the ene, right, or I, if you need to. That's naming. All right. Next, my favorite. So, and I noticed I missed a letter, so there should be an I in your answer key, it stops at H, does it, or did I correct
It
yours
stops
already?
H, but
Yeah, so there should be an I, I'm sorry. So the I is over here. Okay, so we'll do it in order. So first and foremost, you don't even know what you're starting with, which means you actually can have multiple answers to this. So A, which you want to do your first structure here. So basically what you're giving me is what do each of the letters correspond, right? Which structure does it correspond to? So A has a molecular formula of C4H10. So what would that look like? I mean, like I said, there could be two possible answers. So it can be butane, right? Or it could be, what's the isomer? Same molecular formula. Take one from the end and put it in the middle. So it could be 2-methylpropane. And I mean, it wouldn't be wrong. You could start with either of them and go through the process and get all the correct answers. You can do it for either or. Okay? So I will do the isomer. And again, for yourself, you can do the other, right? For practice. Okay? All right. So what would I do? So A is 2-methylpropane. You don't have to name, by the way, just draw the structure. So then I'm going to take A and I'm going to react Br2, some UV, okay, 1 mole of it, and then I'm giving you the molecular formula C4H9Br. So what has happened there? I added the Br, and where should I add that Br?
To a primary end.
Yes, sir. Right, you always add to the most substituted. Does that make sense? So what would happen if this was butane? Where would it go?
Either the second or third part.
Right, it would just have to be in the right middle. Either one is fine, but you would not want to put it at the ends. They follow Mark's rule. Right? So you see how you could practice, right? It would still give you answers there. All right, so now you got B. So then to B, you're going to add KOH. Oh, and I left out heat. I'm sorry. So could you add a little triangle? Should add heat there, because look at the formula, like C4H8. So I've lost the bromine and I've lost the hydrogen.
So you have the double bond.
So I have to have a double bond, right? So now where would my double bond be? Right, the Br is gone. Right? Either.
Yeah.
They're all the same, right? So it doesn't matter. But they're going up, to the left, to the right. They will all give you the right answer.
If it was with the butane, it would be
If it was with,
in the middle.
yeah, then in butane it would be, right, since you put the Br here, it would go this way,
Okay.
because those are both secondary, so there is a preference. All right, so then C goes to D, and it's reacting with what? I drew it out, but that's really just the RCO3H, right? That peroxycarboxylic acid. And what did that give you?
Epoxide.
Epoxide, right? And again, the epoxide is where the double bond is, right? So. Makes sense? Did I put it? Oh, I'm sorry. Forgot that. Sorry. Right, so the epoxide is here, and then I'll have my 2 methyls, right, as substituents on my epoxide. Does that make sense? So the epoxide is here, and then the 2 methyls. So what would it look like if it was the butane? The double bond is here, so now what should I have? The epoxide, and then a methyl on each side, right? See how you can really do it either way. I'm sorry if I'm blind. Because I'm a lefty, I always have to turn. Yeah, lefties.
We're all lefties right
Okay.
here. All Italians.
Does that make sense though? So again, epoxide, right? And then D to E, what's happening there? So I'm taking my epoxide and I'm reacting with that sodium, right, alkyne, which is going to do what?
Should take off that oxygen. Break that oxygen.
It's not going to take off the oxygen, it's going to do what? It's open it up, right? The nucleophile is going to tap in the side that is least substituted, right? Because that's part of the rule here. So what you're going to have now, right? You're going to have your 2, right? And the OH. And then over on this side, right? You're going to have the carbon. Oops. It's the bond there. And you're going to have the carbon. Does that make sense? So these are your 2 substituents, right? Right, the carbon, the 2 that come from your epoxide, and then you're adding 2 carbons per your nucleophile, right?
Where is the attack on butane?
Yeah, so if you had the other one, it would not matter because both sides have a methyl group, so you could attack each side. But again, you would open it up, and then you would have the OH, right? If you attack on this side, the nucleophile, which doesn't matter, you can do either side, excuse me, right? But then you would have a methyl again, and then the new thing. Does that make sense? So again, you can just make sure you got all the carbons, right? Methyl, main carbon with the OH, right? And then other carbon and methyl. And then again, the nucleophile happens to have 2 carbons, so. Does that make sense how to do these? So that's E, so now let's go to F. F, we gotta go back to C, and we are adding HBr peroxide. So what does that give us?
It gives it BR on the primary on the very end.
Does the double bond open?
No, no, this is with peroxides.
Right, so you're, again, going back to C, right, and considering that, right, where would I add or what would happen, right? Some mechanisms you would open the double bond, right, but this one is actually going to add here, HBr peroxides.
It has the allylic end, so, or the,
That should be F. Again, you've got to consider because there's 3 different reagents that could be in that place, so you could get 3 different products. But that's F, and then F goes to G, and G is NaOH, and this time it's not a mistake that there's no heat. So without heat, what does an NaOH do? Substitution, right? So wherever the Br is, you're going to now have an OH, right? So this is acting like a nucleophile if there is no heat. Okay, so make sure that for the KOH between B and C, you put a little triangle so when you're studying, you don't get confused because I left out the heat. That was my fault, so make sure you put it in because otherwise, when you're studying, you might be like, why is that one doing that and NaOH without the heat over down here doing something else, right? So this should be no heat, and that's right. So that was my mistake, so I just want to make sure, and I'll make sure the exam, of course, is correct. So G, and then G then makes H. So what would H look like? So I'm taking that alcohol, and I'm doing what?
you make an aldehyde with it.
That's not PCC, though.
You have
The carboxylic acid, right? If it was PCC, it would give you the aldehyde.
This is Jones reagent.
Okay, and then now I'm going back to C again to give the last one I that I left out of your
what were the
answer spaces there.
Butane was right, for F, G, and H? Or just,
Well, now I've kind of passed the point of
I just want
the,
to H.
huh?
I just want to go to H.
Dial.
Well, I just have to go back to C, and C was like this, right? So then again, if you did, the BR would have been here, you would replace that with the OH, right? And then that would still be primary, so it would give you, right, the OH. But the double bond would just be in a different place. Does that make sense? It's just really where the double bond is, because everything else is really, again, same reactions, right? The BR. Oh, sorry, this is. Now that we did the butane, you can't really practice that. What are you going to do to practice? Pentane, propane, pentene. I mean, you know, you name it. Like, you can really come up with whatever starting material you want, and then follow the reagents, right? Question? Question?
The virgins.
Which one? Check this. The O from the epoxide is, and it could be on either side. It would be on the opposite side as the nucleotide. And that is a sen, so you have to make it cis. Make sure they have wedges, both wedges, or both dashes. Okay. So do you think you're going to see this one on the exam?
maybe not this
Yeah,
one,
right.
but
Hmm?
something of it.
Yes.
I think he'll be most certainly on the exam. Love this. Okay, and like I said, this question, each one is worth 2 points. So that's like 16 points right there. It's a big chunk of your grade. You don't want, to get stumped on one like this. So practice this as much as you can, right? Make up your own A. As long as, you start with an alkane and you go through the process. It doesn't matter if it's pentane, if it's propane, if it has, a methyl group or not. It's always going to give you that sequence of reactions. Does that make sense? So practice. There's no reason you shouldn't get 100 on this one. All the points. All right. Then multiple choice, and it won't be these, but again, you want to think about, right? Because I like the concepts. I just may change it slightly, so you have to understand each question. So A says, what reagent is necessary for the conversion of 4,4-dimethyl 1-butanol to 4,4-dimethyl 1-chloropentane? So what are we doing? We're taking an alcohol and we are
OH group and adding a CL.
right, adding a CL. So what could possibly give me that?
4.
So we talked about HCl. Is HCl good for substitution?
No.
No,
Nay.
right? So,
It'd be
right, this is definitely a good one, right?
Yeah.
We talked about that one.
Is it SN2 though?
Mhm.
Yes, because 1 pentanol.
But the problem is the rearrangement, because you have 4,4-dimethyl, so there's a potential for substitution. So you don't want NaCl, because these kinds, right, so we don't want that. So PbCl3, we didn't have it in lecture, but we had it
We have PBR.
PbR3, right? So potentially you can do the same reactions, just having chlorine, right?
So yes, 5.
So So the answer is 5.
Why?
Because they don't rearrange.
Yeah,
Yes.
PBR3 doesn't never range.
And then it's SSCL. Or HCl does because you would rearrange it.
So it's only
So 3 and 4. All right, so what about B? Which of the following compounds would yield a ketone when reacted with the chromic acid, right? Or the dichromate in this case here. So which one would give you a ketone? So it would have to be a secondary alcohol. So what can I rule out, right?
3.
Hmm?
It is 3.
Yeah,
Three.
so
Yeah.
the answer you
6.
think is 3? Or you're ruling out 3?
Ruling out.
Ruling out 3, because that's an ether, it's not even an alcohol, so it's
Yeah.
not gonna undergo oxidations, right? What about phenol? Phenol's that benzene with the double bonds. Remember, phenols don't react like other alcohols, they don't undergo oxidation. So you can rule out the phenol also, right? And this is gonna be, a ketone has to be secondary. I
So-
said that already, so which one is out also?
Get rid of 2.
2 and 5, right? We ruled them all out. So isopropyl, remember, looks like this, right? This is a secondary. These are both primaries. Right, so what if the question said which one yields an aldehyde?
It would be
Then
the one
either
that's
one of
on the
these,
primary.
right?
It's gotta be on the primary.
Nope.
They're
None
shared.
of the above, why? The reagent doesn't give you an aldehyde.
No, it always gives you a sheet trick.
I hopefully walked off screen as I did that evil laugh. That would be so dramatic for the student watching it. But does that make sense? So again, I like the questions, right? You know that I tend to do that, but you have to understand, not just memorize the answer, right? Because this is specifically asking you about ketones, but I can change it to aldehydes, and then, of course, if I actually wanted you to have an answer for primary, then I would have to switch this to PCC. All right, so what about C? Which of the following methyl groups will show the most downfield? Remember, we haven't had a question on the NMR or IR, but don't forget about that. So the most downfield, right, H, NMR chemical shift.
It's the one that's, the ones that are most shielded or least shielded.
Least shield is going to move far left.
So downfield is towards 12, right? So if you were thinking about the scale, right, 0 to 12 is my scale, right? So downfield is this way.
Is it
You have to be
Is it one?
So there has to be what if you're downfield?
LA?
Has to have something electronegative, right? So which ones can I rule out?
4 and 5.
Yeah, right? That's gone.
Is it methyl
That's
iodide?
gone. Does that make sense? So I mean,
Yeah.
but now all of these have technically.
It's 1? Is it 1?
So which one would it be?
Is it methyl iodide?
Well, the most shielded is to the left, and the least shielded goes to the left.
So the D shielded is to the left, which means there's an electronegative atom. Highly shielded are the ones that don't have any electronegative atoms in the molecule. I know it's a little bit confusing, the terminology, but the downfield towards 12, you would want something electronegative. So the question is, which one is more electronegative, iodine or oxygen? Periodic table's right there. Which one is more electronegative? Oxygen, right? N, O, and F are the most electronegative atoms on the periodic table. So I is also out.
So it'd be the methyl
So now the question is, does the alcohol versus the ether, which one is more electronegative, right? Or more negative based on the structure?
all.
The all, because it's going to take the electrons, right? Does that make sense? How to think about this question. And again, I could do which one is most upfield. Same question, same answer.
CH4.
Sorry, I'm getting lots of emails today. Got a lot going on apparently. So does that make sense? So then the answer would then be this one. So see how, I mean, a small change, right, in the question, but again, because it's really about thinking about the concept. Okay, D talks about how many signals would you get for this molecule, 2-chloro, 3-methyl, 2-butene. So how many peaks means what? How many types of hydrogens do I have? So again, you might want to draw out what this structure looks like. So it's butene, 2-butene, 2-chloro. Right, so that's what the molecule looks like here. So how many kinds of hydrogens do I have? Right, so this is a CH3, this is a CH3, this is a CH3. These don't have hydrogens, would you agree? Right, they already have 4 bonds. Are all of these CH3s different from each other is kind of the question.
No, the other two are the same. Those two.
So this is one kind, agreed? The question is, are these different?
No.
Yes, remember the double bond does tend to have this, the ones that are trans, right? Cis trans. Double bonds are tricky. If it was a single bond, right, it would be different. So there's actually 3 kinds, A, and then B and C. Now you can't tell anything. Alright. Then the last question is, which combination of reagents would afford you the highest yield of methylphenyl ether? So this question has to do with that William ether synthesis. Remember, William ether synthesis has a requirement, right? What is it? A primary, small, right, halide. That makes sense? And then you're going to combine that with, right, that ion, right? But that doesn't matter, right? It's going to have a carbon chain, but that doesn't matter if it's big, if it's small, if it's, you know. But the halide is the part. So what combination would be best? And I want to make, right, a methyl on one side and a phenyl on the other. So which side should be attached to the CH3, or what should be attached to the CH3, right? Because you're splitting it where the oxygen kind of is, right? To think about both sides. So what should be with the CH3?
Sodium or iodine.
Right? Iodine, it should be primary and small. This is even better than primary because it's methyl, right? So C, and then C would have to be combined with what? Then the other side of the molecule,
Yeah.
right? And this is C6H5, by the way.
So it's
C and D.
C and D. That makes sense? So William ether synthesis, there is a requirement. Last 2 questions are synthesis questions. So you're given the starting material and asked to give the reagents to give the specific product there. Right, so starting materials product. So what should I do with A?
Add a
So
chlorine.
what is the only thing I can do with an alkane?
Halogenation.
Yeah, right, so halogenation. And again, you can pick, you know, Br2 is fine, or whatever, you know, you want to put in, UV. So then it puts in the bromine wherever you want, since this is cyclic, right? If it wasn't cyclic, it would put it on the most substituted. But since it's cyclic, you can put it anywhere. All right, so I know that, and I know at the end, I want it to have an OCH3, right, coming off of my ring. So instead of the Br, so what should I do?
Add
CH3O negative sodium.
Hit the double bond.
Oh, that's not a small.
I mean, I have lots of options, so
And then
we
we
just did one. The William ether synthesis is a possibility, right? Because this is an ether. So if that's so, what would I want to do?
You just add a CH3.
So what would I have to, I don't want to add the CH3 now, that wouldn't help me. The CH3 is going to be the last thing I'm going to add if I'm doing a William ether synthesis, because the CH3 is going to be added as what? CH3, small, I should have erased it, right? A small halogen, right? But what would I have to come with? That part, right?
Oh, so you'd have to eliminate the bromine and get an O first.
So this would have had to be formed already. So how do I go from this to this? 2 steps.
NaOH.
So I need an AOH. Heat, no heat. No heat, right? Because what do I want? A substitution, right? I don't want it to go to the double bond, even though I could, but that's going to add an extra step. And then now, how do I get this? It's another step. Yeah, Na metal, right? The little knot, or you can write out Na metal. Okay, so that will give you that, and then to that you add, and you get your ether. It is not the only way you can do it, but okay, like I said, I will look at yours, and if you come up with a suggestion that makes sense, as long as it has the steps are leading towards it, giving you the correct products, and you have to give me the reagent, give me the intermediate, then next reagent, intermediate, until you get to the end. So don't just give me a list of reagents. That's not full credit. You get some credit, but it's not full credit. So what about in B? What am I trying to do here? Can only do one thing. What is it? So everybody should get at least a point, right? Right? I don't want anybody, again, just where do you put it, right? In the middle, because you go to the most substituted. Right? And then what do I want eventually is a double bond L, right? So again, what do I need? An
NaOH with heat.
alcohol, right?
NaOH with heat. Just go ahead and get the double bond.
PCC or chromic acid, they both would give you the same product. Very easy, right? Again, you could have done double bond, added the OH. I mean, there's different choices, but it gets hard when you have to decide if you want the alcohol here and the bromine is here. Then you got to think about it. You do have to do the double bond, do the least substituted reagent, right? So again, practice. Change this up. Send it to me. Is this right? Okay, or come by my office and say, is this right? You're very smart, but you need to practice, right? And when you're very smart, you have to practice. I practice all the time. To look this smart, you gotta practice a lot. All right, so now CH3, excuse me, alkyne, so triple bond, right? So we're now kind of starting from a reaction sheet, which is 7, right, chapter 7. So this is kind of nice because it opens up possibilities here, but maybe you don't like possibilities, but hopefully what you see is you have 2 carbons, and I'm going to how many carbons?
4.
Yeah, so I'm going to have to find a way of making, right, a carbon-carbon, a new carbon-carbon bond. And there's really only one reaction with alkynes, which is?
Acylation of a C.
So it should be, which one? Again, chapter 7.
NH2. NaNH2.
Yeah, the alkylation one, right? NaNH2. And then the NaNH2 is the first reaction. Okay, that's going to give you the ion. right? And of course the sodium is there too. Okay. But it gives you the ion, and then you can add what? Which is the next thing, number 2, on that same reaction, is R, right? With the halogen. So how many carbons do I want to add?
2.
2, but I can't do them at the same time, right? Because it's 1 on each carbon. So I have to do 1 first, right? Does that make sense? And then it's going to extend my chain where the ion is, this side. And then what do I have to do?
Do it again.
Do it again. Right? NaNH2. Right? And I'll combine just for fun. Right? So now you already had the first CH3. And now I'm going to have another. Does that make sense? But I have a triple bond, and that's not quite what I want. So again, that same reaction sheet, there should be some reduction options.
H2.
Notice that I want the trans product.
NaNH3.
NaNH.
So you just, the key here is that you can't do it all in one step, right? So you identify the reaction, but since you're adding a carbon on each side, you do have to do it twice. Now you could combine this and this together the first time too. I just did it separate to kind of walk you through question. Yeah. All right, does that make sense? And then one more, number 8. So number 8, you're starting out with ethane. You're making this alcohol, which is butanol. So you are also increasing the chain, right? But you're not really starting with the triple bond. You're starting with the alkanes. What's the only thing you can do?
Halogen.
Everybody to get a point. That's a point. So we get Cl2, UV, or heat, or something like that. And since this is, both carbons are the same, you just put it in whichever one you want. Be in the first carbon. And then what else do I have to do? Because I want to, you know what? This mechanism, BR, does work better. It would still work if you did chlorine. I would not penalize, but that kind of gives you a clue. What would you want to do there? If I want to exchange my chain, I don't have a lot of options. I don't have a triple bond here, right? This is not a cyanide, right? So what's the other option we've learned so far? Chapter 15.
You could,
Right? Remember that those organometallics, and if I have the Br there, which organometallic am I leading you towards? Magnesium. So that's why I changed. Okay, it would still work with the chlorine though. Okay, you can make Grignard MgCl, but Br is usually what more common. Okay, so you're going to have this, and again, it's an ether, right? And that's going to give you the salt part with the Mg. Right, Br. And again, remember that what that's doing is making your carbon, right, an anion. You don't really have to draw that when you're doing it, but I'm just showing you that's really what I'm going after. So that's one side, right? What's the other side? Right, I'm also have to start here. Does that make sense? So you have to start with ethane only. I didn't read the whole question because I know we're a little short on time, but it says all reagents and molecules, right, have to come from the ethane. You must use ethane as the only source of carbons. So I have to kind of do this again, right? And have another. Okay, so now what's going to happen on that side? Which reactant combinations would be used for the Grignard?
Lithium.
The butyllithium would be this same part. So we've already have our organometallic. We have to know what would we attack to give us 2 carbons and an oxygen. 2 carbons and an oxygen. That's my pattern. 2 carbons and an oxygen. That comes from a
NaOH.
copper lithium is this part together.
NaOH.
I don't want this. Not NaOH. NaOH. No. I mean, are you saying for the next step to give you an alkene? Yeah, that's true. You do want an alkene, but the goal is to do what? This has to transform into something that this is going to react with.
Would it be the,
2 carbons and an oxygen. That's the key. 2 carbons and an oxygen. What gives you that pattern? Epoxide. Right? So you need a double bond, and you want to get the epoxide. What's the reagent?
RCO3.
Yeah, RCO3H. Right? And now you can combine these 2 together. Right? And remember, this is acting like a nucleophile that's going to attack and open your ring. Now you do want O, right, H, an alcohol. So you do have to add, right, H plus here, right, or something like HCl in water, a dilute acid, to complete your alcohol. Right? But this is going to give you 1, 2, 3, 4, and then the alcohol on this side. Isn't that your product? Right? This is coming from here, and I'm attaching to 2 more. Right? And when you open, the OH is over here. Is that not my product? Exactly my product. The end. Right? So the key here is that you had to use ethane as your starting point for both. So that's why you kind of have them going, right, into 2 directions and then coming together at the end. Right? But Grignard plus epoxide is really your, right, the connection I was trying to have you make there. Right? And of course, don't forget there will be an additional question on IR and NMR, and there will be 1 question together. You'll get an IR, you'll get an NMR, you'll get the molecular formula, and you have to give me the structure. Okay, and don't forget the parameters, just like the
extra credit.
Just like the extra credit, but I'm also going to give you an IR to help you. The IR is just going to be additional information to help you figure out the functional group. So it should be, you know, a helpful thing to have the IR, not to make it any more difficult.
And we're supposed to draw the structure. We don't have to know the
You're going to have to draw the structure and give me the name, just like that.
What was the name for this one?
So that should have been 3 pentanone, 5 carbons.